Construction operates on extremely tight profit margins. A single day of unexpected delays on a major project can hemorrhage thousands of dollars, completely wrecking a budget before the foundation is even poured. Every site development begins with a land survey to understand the terrain. However, this crucial first step is notoriously slow, often creating a massive scheduling bottleneck right out of the gate. Traditional surveying requires crews to physically walk the property. They have to drag heavy equipment across steep slopes, unstable soil, and dense, unforgiving brush. It is a slow, physically demanding, and inherently hazardous process. Depending entirely on these manual, boots-on-the-ground methods locks a project into a sluggish timeline. You practically guarantee delays before a single piece of earth-moving equipment arrives on site. To speed up the process, the industry turned to the sky. Specifically, using standard drones to take hundreds of overlapping photos to create 3D maps, a process called Photogrammetry. Photogrammetry works well for bare surfaces, but it has a specific engineering flaw on raw land. It relies on passive light. The camera can only map what it physically sees. If a site is covered in trees, photogrammetry maps the top of the leaf canopy, not the dirt beneath it. This graphic compares two dominant technologies. On the left, photogrammetry passively reconstructs visible geometry. On the right, LiDAR uses active laser pulses. The key difference is below. While photogrammetry struggles with canopies, LiDAR penetrates dense vegetation to find true ground elevation. If developers mistakenly use the top of a tree line as the ground elevation in their planning software, their earthwork and material volume calculations will be off by millions of cubic feet. Planning foundational earthwork on superficial data leads directly to expensive surprises the moment excavators actually begin tearing into the soil. Drone-mounted LiDAR provides the engineering-grade terrain data required to bypass the canopy problem entirely. Instead of taking pictures, a LiDAR sensor fires hundreds of thousands of rapid laser pulses per second directly downward toward the earth. Because laser light is highly concentrated, a single pulse can hit a leaf or a branch, register that strike, and still partially continue downward to strike the solid dirt below. This is the core mechanic of multiple returns. Specialized mapping software filters out those early strikes from the foliage to isolate only the final returns, the bare earth. By actively measuring the terrain through the brush, this technology removes the hidden variables that traditionally derail site budgets. Firing lasers is only half the equation. To build a reliable map, the drone must know its exact spatial orientation, relying on a high-precision positioning system called RTK, or Real-Time Kinematic GNSS. This datasheet outlines the results of that positioning. Looking at the crosshair icon, RTK-enabled LiDAR produces dense point clouds and digital elevation models with an absolute accuracy of 1 to 5 centimeters. It captures this precise data at an astonishing pace. Topographical surveys that once required human crews several weeks to complete are now finished in a matter of hours. The final product is a pristine digital elevation model, or DEM, providing a high-fidelity bare earth canvas for engineers to analyze. LiDAR replaces a sparse grid of human estimates with a comprehensive, undeniable digital twin of the entire property. That digital twin drives one of the most critical financial calculations in construction, the cut and fill analysis. This visualization shows the analysis. Red zones highlight elevations to be cut, while blue zones show areas requiring fill dirt. Precise volume calculations prevent contractors from miscalculating material orders or excavation time. As this graphic shows, the terrain data also allows teams to identify hazards very early in the planning process. Under the Risk Assessment panel, engineers can pinpoint flood zones, erosion risks, and unstable slopes long before deploying heavy machinery. These dense, classified point clouds are then exported directly into the standard CAD and building information modeling software used by architects and civil engineers. Implementing drone surveying yields a routine 80 to 90% savings on traditional labor and field time. It also keeps human workers off unstable ground and out of hazardous environments entirely. Integrated LiDAR transforms the drone into a high-precision surveying instrument. For developers protecting their margins and schedules, this data provides the measurable certainty required to stay ahead of the competition.